Hey guys, welcome back to AP Chemistry. We're starting Unit 4 now, which is Thermochemistry. A lot of this is going to sound familiar to you, but of course we're going to go a little bit more in depth than we were able to do in general chemistry. So we're going to look at endothermic and exothermic energy transfers, the difference between kinetic energy and potential energy. Then we're going to talk about heat capacity and specific heat, and how to use calorimetry to describe the type of substance we're working with, or how much heat is exchanged between the system and the surroundings. And then I'm going to show you new ways to work with Hess's law, and of course we're still going to work in the old ways with Hess's law too. So that's where we're headed for this unit. In this podcast we're just going to focus on energy. So let's get started then. Energy has many different facets, but basically energy is the ability to do work. So the more energy you have, the more work you can get done. Does that sound familiar? And energy is always conserved. That's the first law of thermodynamics. Law of conservation of energy. And so we're going to be using that concept quite a lot, that energy is always conserved. We also know that energy is made of two things, heat and work. You see, sometimes the energy that you spend to do work transfers into heat, and whatever goes into heat is not going into work. Yeah, you're probably familiar with that too from sports and things. And then energy is also a state function. And since this is probably the newest concept, we're going to start with the state function, and then we'll focus in more closely on the ideas of heat and work. So let's look at what a state function is. Maybe. There we go. Oops. Here we are. A state function means that it's independent of the process or the path. So what we mean by that is that the amount of energy or the energy change is going to be the same no matter how you get there. So let me give you an example. Let's draw a mountain like, oh, looks like devil horns, like Pikes Peak, right? And so we're going to start here in Falcon, and we're going to go to the top of Pikes Peak, all right? But one of you guys is going to hike up the mountain on bar trail. So put your backpack on and hike up the mountain. Okay, now I am lazier than that. So I am going to get on the train and take the train up the top to Pikes Peak, right? Because I'm not hiking all that way. So here's me in the train. But then some of you clever folks, you know, you got connections, and one of y'all gets in the helicopter. Better put a tail on it and some blades. There we go. So now somebody's going to go in the helicopter up to the top of Pikes Peak. So we want to know, if we all started in Falcon, who went the farthest? Who has the greatest change in their position? Well, if we all started in Falcon and we all ended up at the top of Pikes Peak, then we all went the same distance. Pikes Peaks, yeah, Pikes Peak, there we go. Yeah. So if we all went the same distance, then that's kind of like a state function, right? That it doesn't matter how you got there, what matters is the overall change. Doesn't matter how we get there, we just need the beginning and the end state. All right, so let's look at heat then. Heat is energy that will be transferred from one object to another because of their difference in temperature. And heat will always move from hot to cold, right? From high heat to low heat. So work is a force that's acting over a distance. That's why the pathway is important, because distance is important. So here's the physics formula for it. Force times distance, right? Or what we call in physics displacement. So the amount of work you do depends on the size of the force and the distance across which that force is applied. So an energy would have to be used to move an object against a force, right? Like if we have a positive charge, we want to move a positive charge closer, then that goes against the electrical force that repels these two charges. You would have to put energy in to make that happen. So that's an example of work. Let's look at work in a chemical process. Okay, because in chemistry, the force is often applied by pressure. So let's have a container here, and we're going to put a lid on this container, but it's a lid that we can move up and down like a piston. All right, so we can push it down farther into our container and squish our gas molecules inside here, or we can raise it up higher and give them more space. All right, got that picture? So now let's define pressure. Pressure is force times area. All right, where the area is, this circle, pi r squared. And then the volume of something is going to be pi r squared times whatever the height of our cylinder is. That's volume. And so we can define the distance that we move this as basically our change in the height of our cylinder here. So if we take the volume divided by the area, so pi r h divided by, pi r squared h divided by pi r squared for the area, then it's this piece right here, the height. That's the difference that makes up the distance of work that's done. So what we're looking at here really is that force times distance for work, force times distance by substitution necessarily will be pressure times area times the change in volume divided by area, and that simplifies, area canceled out, that simplifies to the pressure times the change in volume. Now notice there's a negative sign here, right? Because pushing it down is work that you have to put energy into, and moving the lid out is the natural way it would occur. And so just by the definition of what energy goes in or energy comes out, endothermic and exothermic, that's why there's that negative sign there. So in chemistry, we often calculate work this way, by multiplying the pressure by the change in volume, so at constant pressure. So what we're saying is you use your gas laws to calculate the work, right? And these units are going to be pressure would be atmospheres, change in volume would be liters, so liters times atmospheres has this abbreviation LATM, or you can put a dot, liters times atmospheres. Okay, so that's the units for pressure in working with gases in chemistry. Let me clear that out. So we're going to look at now two forms of energy. You're already familiar with this. Kinetic energy is the energy an object has due to its motion, right? Like a swing will be moving its fastest. Let's draw a swing set, and here's our swing. And the kid on the swing. Wow, poor kid. There you go. Hold on. So when we're up here, we have high potential energy due to the position or condition relative to the ground, right? And then down here at the bottom of the swing is when we're going the fastest, so we have maximum kinetic energy here. And then we go back up to the highest height, and that's where potential energy is at its greatest. And of course that makes it go back down and pick up speed again. So here we would have zero kinetic energy at the top of the swing because it stops going up and then starts going back down again, right? So that's how potential energy and kinetic energy work. One is due to motion, one is due to its position or its condition, like a spring if it's stretched or compressed, right? That's its condition. And in chemistry, we have these same things. Kinetic energy we call temperature, because the kinetic energy of all those particles is going to release some heat, right? Some of it translates to heat. We call that temperature. And then potential energy in chemistry is energy that's stored in the bonds between atoms. So in this molecule, there would be a certain amount of energy stored in this bond and a different amount of energy stored in this bond. But then we would have more energy in a double bond than in a single bond. So that's how we work with energy in chemistry. You're going to get to see a whole lot of these different examples.
Susan Thomas, can you please come to the front office, please? Susan Thomas to the front office. Thank you.
Okay, now let's work with an example of kinetic energy problems. I just showed you a slide that gave you the equation for kinetic energy. Should we go back and look? Here it is, 1/2 mv squared. All right, so we're going to use that, 1/2 mv squared. That would be then mass times volume, velocity squared. The wrong v. This is a lowercase v. All right, so let's list what we know in our problem. We have a 45-gram golf ball, and we're going to need to change that to kilograms. So 0.045 kilograms. And it's driven off of a tee with a velocity of 61 meters per second. Well, thankfully that's already metric, and that's in our units we need, so we're good to go. Let's calculate the kinetic energy that was transferred from the golfer to the golf ball in this drive. All right, so remember our formula is 1/2 times mass times velocity squared. Okay. Kinetic energy is equal to 1/2 times the mass in kilograms times the velocity, and the velocity needs to be squared. So now grab a calculator. So we take 1/2 times 0.045, and then don't forget to square the velocity, and I get a total kinetic energy of, whoa, wrong spot, 83.7225. Now, just because I get all of this stuff in my calculator doesn't mean I get to keep it all. I have 2 sig figs, 2 sig figs. All right, so we're going to call that 84 kilogram meters squared per second squared, which is the same thing as joules. So 84 joules of energy. So that's how we work with kinetic energy. That's not so bad, huh? It's just a formula, right? So start with what you know, put it into the formula, and solve. You have a couple of homework problems like that. So I know you'll be able to handle those well. Let's try one with potential energy. This same golf ball, the one that had a mass of 45 grams, which is 0.045 kilograms, that golf ball achieved a maximum height of only 150 meters. All right, so let's put the height there, 150 meters. Now we need to calculate the difference in kinetic energy and potential energy and give a possible explanation for this discrepancy.
Mrs. Thomas.
Okay, so the easiest way to approach this problem is if we had a formula for potential energy. So let's go back and find it. Here it is, mgh. All right, so potential energy is the mass times acceleration due to gravity times the height. And some of you may know already, acceleration due to gravity on Earth is 9.8 meters per second squared, and then the mass is, in kilograms, 0.045, and the height is 150 meters. All right, well, let's calculate potential energy then using this formula, mass times acceleration due to gravity times the height. And that's meters per second squared, and then the height was 150 meters. All right, calculator time. So 0.045 times 9.8 times 150. Now I get 66.15 kilograms, and meters times meters is meters squared over second squared. Well, that's a promising sign, right? That we ended up with, oh, wait, I'm doing this on kinetic energy slide. Sorry about that. There's potential energy. Yeah, so we ended up with the same units, and we should. So we get 66 joules, and kinetic energy was 84 joules. So what do you suppose could account for this difference of how much? If I use the non-rounded figures to find the difference, I get 17.57. So we'll call that 18 joules of difference, right? What accounts for the 18 joules? Where did it go? Because remember, the law of conservation of energy, first law of thermodynamics, says that kinetic energy has to be the same as our maximum potential energy. What happened to our 18 joules? Remember, not all energy gets to be translated into work. So some of this was lost due to heat, or we call this friction, right? The air resistance of the ball going through the air, or maybe some of the heat between the golf club and the golf ball itself. So not all of that energy actually went into doing work on the golf ball. Some of it was lost due to friction and air resistance. So that's a good explanation for the discrepancy. The energy is still there, it's just not in a useful form, which is what we use to do work, right? So that's how we work with potential energy and kinetic energy. The last thing I want to talk to you about is internal energy. This would be the sum of all kinetic and potential energies of a system's components. So for a system, if we're only looking at what it is made of, then we would add up all the kinetic energy and all the potential energy. We know the change in energy. Remember, delta means final minus initial. The change in energy has to be the same as what was gained by the surroundings. So energy could be transferred between the system and the surroundings, but the overall amount of energy is going to remain the same. If you find a positive energy change, then a system has gained energy from its surroundings. A negative energy change means we've lost energy to the surroundings from the system. Remember endothermic and exothermic? Our units for energy are in joules. Just like last year, we had enthalpy in joules, right? And 1 joule is 1 kilogram times 1 meter times 1 meter per second squared. So it's meter squared over second squared. Other common units would be calories or British thermal units, BTUs. The calorie is the one that you'll need to remember. Don't worry about BTUs. And if you're ever asked about BTUs, you'll be able to look up how many BTUs are in a joule or a calorie or whatever. The calorie is specific to water, right? It's the amount of energy to increase the temperature of 1 gram of water by 1 degree Celsius. And 1 calorie is equal to 4.184 joules. And if you see a capital C, that means kilocalorie. So that's 1,000 calories. That's commonly used on food labels. So, pay attention to your units, use the formulas, and pay attention to the direction that energy is being transferred, so you know if it's positive or negative, endothermic or exothermic. So that leads us into our next podcast. Okay, be watching out for endothermic and exothermic.